Deep within the vast expanse of space, a cosmic ballet unfolds. Stars are born, they shine, and they eventually die. Their demise, however, can be a breathtaking spectacle. It can also be a creative force. From the ashes of dying stars arise protoplanetary nebulae, ethereal clouds of gas and dust that serve as cosmic cradles for new generations of stars and planets. Protoplanetary nebulae are relatively short-lived phenomena. They exist for a fleeting moment in the grand scheme of stellar evolution. Yet, they provide invaluable insights into the processes that lead to the formation of planetary systems. Understanding these celestial objects is crucial for unraveling the mysteries of our own cosmic origins. These nebulae are not simply remnants of dead stars. They are vibrant and dynamic environments. They are filled with complex molecules and swirling dust grains. It is within these cosmic clouds that the seeds of planets are sown, and the potential for life itself is nurtured. Join us as we embark on a journey to explore these celestial wonders. We will delve into their formation, their characteristics, and their profound significance in the grand tapestry of the cosmos. To understand protoplanetary nebulae, we must first grasp the life cycle of stars. Stars are not eternal. They are born, live, and eventually die. Their life cycle is a fascinating tale of nuclear fusion, gravity, and the relentless passage of time. Stars form from collapsing clouds of gas and dust. Gravity pulls these materials together, increasing the density and temperature at the core. Eventually, the core becomes so hot and dense that nuclear fusion ignites. Hydrogen atoms fuse to form helium, releasing an immense amount of energy. This energy counteracts the inward pull of gravity, creating a stable star. For millions or even billions of years, a star will continue to fuse hydrogen into helium in its core. This is the main sequence stage of a star's life. Our Sun, for example, is currently in its main sequence. Eventually, however, the star will exhaust the hydrogen fuel in its core. As the core runs out of hydrogen, the star begins to evolve off the main sequence. The details of what happens next depend on the mass of the star. For stars like our Sun, the core contracts and heats up. This causes the outer layers of the star to expand dramatically, forming a red giant. Red giants are huge and luminous. They are also relatively cool compared to their main sequence counterparts. As a red giant expands, it loses mass through a powerful stellar wind. This wind carries away the outer layers of the star, creating an expanding shell of gas and dust. It is this shell that we call a protoplanetary nebula. Protoplanetary nebulae are relatively short-lived phenomena, lasting only a few tens of thousands of years. During this time, however, they undergo dramatic changes. The intense radiation from the central star ionizes the surrounding gas, causing it to glow. This glow is what makes protoplanetary nebulae visible to us. The shape and structure of a protoplanetary nebula are determined by a complex interplay of factors. These include the mass and rotation of the central star, the presence of magnetic fields, and the interaction of the stellar wind with the surrounding interstellar medium. As a result, protoplanetary nebulae come in a wide variety of shapes and sizes. Some protoplanetary nebulae are spherical, while others are bipolar or even more complex in shape. They can be relatively small, spanning a few light-years across, or they can extend to vast distances. Despite their variety, all protoplanetary nebulae share one common feature. They are dynamic and evolving environments. The formation of a protoplanetary nebula is a dramatic event driven by the powerful forces at play within a dying star. As a red giant star exhausts its nuclear fuel, its core contracts, and its outer layers expand. This expansion is accompanied by a strengthening stellar wind, a stream of charged particles that flows outward from the star's surface. This stellar wind carries away a significant amount of the star's mass, pushing it outward into the surrounding interstellar medium. The wind doesn't flow out uniformly in all directions. It is often channeled by magnetic fields and the star's rotation, creating intricate patterns and structures within the expanding nebula. Imagine a potter shaping clay on a wheel. The potter's hands guide the clay, creating its form. Similarly, the stellar wind and magnetic fields act as cosmic sculptors, shaping the expanding shell of gas and dust into the beautiful and complex forms we observe in protoplanetary nebulae. As the stellar wind pushes outward, it interacts with the surrounding interstellar medium, creating shock waves that heat the gas and dust. This heating causes the nebula to glow, making it visible to telescopes on Earth. The colors we see in these nebulae depend on the temperature and composition of the gas. Section 5. Celestial Showpieces, Famous Protoplanetary Nebulae. The cosmos is home to dazzling protoplanetary nebulae, each unique in beauty. Astronomers study these wonders, gaining insights into their formation and evolution. The Egg Nebula, CRL 2688, is about 3,000 light-years away in Cygnus. It has a bright center with concentric rings resembling an egg. This structure suggests multiple mass loss episodes. These nebulae offer glimpses into star and planetary evolution. With powerful telescopes, we discover more cosmic wonders, enriching our understanding of the universe. Section 6. Dust and Molecules, the building blocks of stars and planets. Protoplanetary nebulae are not just beautiful objects to behold, they are also cosmic laboratories where the ingredients for stars and planets are forged. The dust and molecules within these nebulae play a crucial role in the formation of new celestial bodies. The dust in protoplanetary nebulae is composed of tiny particles of silicates, graphite, and other refractory materials. These dust grains are formed in the cool outer atmospheres of dying stars and are ejected into space by stellar winds. These dust grains act as seeds for the formation of planetesimals, the building blocks of planets. In addition to dust, protoplanetary nebulae are also rich in molecules. These molecules form through a variety of processes, including gas phase reactions and interactions between gas and dust. Some of the molecules detected in these nebulae include water, carbon monoxide, and even complex organic molecules. The presence of water and organic molecules in protoplanetary nebulae is particularly intriguing, as these are the essential ingredients for life as we know it. This suggests that the conditions necessary for life may be common in the universe. Section 7. Unraveling the Cosmos, Observing Protoplanetary Nebulae. Astronomers employ a variety of techniques to study protoplanetary nebulae and unlock their secrets. Telescopes, both ground-based and space-based, allow astronomers to observe these nebulae across the electromagnetic spectrum, from radio waves to X-rays. Optical telescopes are used to capture the visible light emitted by protoplanetary nebulae. These images reveal the intricate structures and colors of these objects, providing clues about their dynamics and composition. Infrared telescopes are particularly useful for studying the dust component of protoplanetary nebulae. Dust grains absorb ultraviolet and visible light and re-emit it at infrared wavelengths. Spectroscopy is another powerful tool used to study protoplanetary nebulae. By spreading out the light from a nebula into its component wavelengths, astronomers can identify the chemical elements and molecules present in the gas and dust. This information helps to determine the physical conditions, such as temperature and density, within the nebula. Section 8. From protoplanetary to planetary, a transformation fueled by stars. As a protoplanetary nebula evolves, it undergoes a profound transformation. The intense ultraviolet radiation from the central star ionizes the surrounding gas, creating a plasma. This ionized gas emits light, giving the nebula its characteristic glow. This marks the transition from a protoplanetary nebula to a planetary nebula. The term planetary nebula is a misnomer. These objects have nothing to do with planets. The name originated in the 18th century when astronomers thought they resembled planets. Planetary nebulae are more symmetrical and less structured than protoplanetary nebulae. The intense radiation pressure from the central star pushes the gas outward uniformly. As the nebula expands, it enriches the interstellar medium with heavy elements. This transition is a brief but spectacular phase in a star's life cycle. It plays a crucial role in the chemical evolution of galaxies, dispersing the building blocks of life throughout the cosmos. Section 9. Seeds of Life, the Potential of Protoplanetary Nebulae. The study of protoplanetary nebulae has profound implications for our understanding of the origins of planetary systems, including our own. These nebulae provide a glimpse into the conditions that existed in the early solar system. They offer clues about how planets form around young stars. The presence of dust and molecules, including water and organic molecules in protoplanetary nebulae, suggests that the ingredients for life are widespread in the universe. As these nebulae evolve and form planetary systems, these life-essential molecules could be incorporated into planets, potentially providing the seeds for life to emerge. Furthermore, the study of protoplanetary nebulae can help us understand the habitability of planets around other stars. By studying the composition and evolution of these nebulae, Astronomers can gain insights into the types of planets that are likely to form in different environments. This information is crucial for identifying potentially habitable worlds beyond our solar system. The exploration of protoplanetary nebulae is a journey into our cosmic origins. By studying these celestial objects, we are not only unraveling the mysteries of stellar evolution, but also gaining a deeper appreciation for the interconnectedness of the cosmos.